we are moving into chapter 3. Today we're focusing on functions. We're going to look at what is a function. We're also going to look at the domain and range of a function, and then also be able to identify the independent and dependent variables of a function. So we have quite a few vocabulary words that we're going to focus on today. The first one is relation. So a relation, what it does is it pairs inputs with outputs. It pairs inputs with outputs. So the most common way that we would see this is with the point on a graph, right? So if I have a graph and I'm trying to figure out what the point is, it looks like this, right? X, Y surrounded by parentheses. What that tells me is that this is a relationship between X and Y. So it pairs an input with an output. A function, then, is a specific type of relation. So a function is a relation where every input has exactly one output. Okay, that means that every X value that I plug in corresponds to just one Y value. That is how we define a function. Next one is domain, and our domain is going to be all sets of X's. So our domain is, it's the set of all X values. Or our inputs. So if our domain is a set of all X values, then our range is going to be our set of all Y values, or our outputs. Okay, and then these last two here, tend to be a little trickier, but we have our independent variable, and our independent variable is our X values or our inputs, and these occur on the X or on the horizontal axis. And horizontal means that I'm going from left to right, side to side. Okay, my independent variable are my X values or my inputs. They're on the horizontal axis. My dependent variable then are my Y values. Oops, it's doing so good. My Y values or my outputs. And these occur on the vertical axis. So up and down, right? And another way that I think about the dependent variable is that the dependent variable is determined by the independent variable. It depends on it, right? So our dependent variable is determined by our independent variable. It can be kind of hard sometimes to remember what things go together, right? So I have this name that I'm going to write on the board. Okay, Roy Dix. So Roy Dix is going to help me remember what goes where. So my R here is going to stand for range. My O is going to stand for outputs. And my Y is my Y values. Okay, so that's my ROI. My Dix part, my D, is going to stand for domain. I is going to stand for input. And X are my X values. Okay, so maybe this will help you remember what goes together. So when I'm talking about range, I'm talking about my output, or my Y values. When I'm talking about domain, I'm talking about input, or my X values. Okay, so now we're going to look at how do we determine if a relation is a function or not. So this is what we would call an input-output table. I have a relation on the top, a set of different points, and I need to decide, is this relation a function or not? So I'm just going to go through and fill these in, right? So I've got -3, 1, -2, 1, -1, 1, 0, 1, 1, 1. So what I'm trying to look for, right, and remember, the definition of a function is a relation where every input has exactly one output. So as I'm looking at this, my inputs are my X values, my outputs are my Y values. Does every X value just go to one Y value? Yeah, it does. They all go to the same one, but that doesn't matter. They're all just going to one value. Yes, this is a function. Ooh. Oh, come on. It was doing so good. All right, every X has one Y. Every X value has one Y value. Okay, so then if I look at this next one, I'm going to fill this all in. So I've got 1, 3, 2, 4, 3, 5, 1, 5, 4, 6. Okay, I want to know, is this a function? Well, I remember that my function means that my every X value only goes to one Y value. So one of the things that I noticed right away is I have a value of 1 here, and I also have a value of 1 over here. So my X value 1 goes to both 3 and 5. So it doesn't have one output, it has 2. So this is not a function. 1 has 2 outputs. So it is not a function. Okay, and then the last one here, pretty straightforward. Looking through, every input goes to one output. Yes, this is a function. So one way that we can compare relations is with input-output tables, or these XY charts that we just did. Another way is with mapping. And I kind of like mapping because it's a visual way to do the same thing that we did with tables, right? So in this first example, my inputs over here, 2, 3, and 4, are mapping over to my outputs over here, -4, -6, -8. And what mapping does is it looks at my input and it draws arrows to the numbers that it translates to in my output side. So my 2 here is going both to -4 and -6. 3 just goes to -6, 4 just goes to -8. So 2 is going to -4 and -6. So this input has 2 outputs. So this is not a function. No, not a function. I look at the second example, I'm asking the question, does every input go to one output? My -1 goes to 4, goes to one spot. 3 goes into 15, goes to one spot. 11 also goes to 15, goes to one spot. This is a function. Now, I had a couple people today that were a little confused because they were like, well, Mrs. Olson, 3 and 11 both go to 15, so it's not a function. So why is the one on the left hand not a function, but this one is? Well, our definition of a function is that my input x goes to one output y. So -1 goes to its own number. 3 goes to one number. 11 goes to one number. So it is a function. Okay, so we have input-output tables, we have mapping, and now we have the vertical line test. So the vertical line test, in essence, tells us I'm going to draw vertical lines through my graph, and if, when I draw my vertical lines only touch one point on my graph at a time, then it is a function. If it touches more than one point on my graph at a time, then it is not a function. So for this first one, I have separate points, right? I'm going to draw a line through that, a line here, a line there. My vertical lines, do they all go through just one point on my graph? Yeah, they do, right? So yes, this is a function. Yes. I'm going to do the same thing with this one, right? I'm going to draw my vertical lines. When I draw my vertical lines, am I just going through one point on my graph at a time? Yeah, there's one point here, I went through it. One point here, I went through it. One point there, I went through it. So on and so forth, right? I'm going through one point every time. So yes, this is a function because I go through one point at a time. But let's say I have this parabola on the left. If I do my vertical line test here, whoop, I think you're noticing the problem already, right? So every time I draw a line, I don't go through one point, I go through 2 points. So this is not a function. No. Get rid of, okay. No, not a function. Okay, this one here, my graph is a vertical line, so my vertical line test, I'm only going to have one line. How many points do I go through on that line? All of my points, right? In this graph, all of my points lie on that line, so this is not a function because I just went through millions of points just all right next to each other. So no, it's not a function. Okay, the next thing we're going to talk about is domain and range. So we've talked about that the domain of our function is all of our possible x values or all of our possible input values. Our range is all the set of all possible output values or our y values. And so I've got this image here, right? My function, y equals 3x. When I put in -2, my input, it spits out -6, my output. So we're going to look at domain and range with these two graphs here. First of all, these graphs each have names. This first graph is a discontinuous graph. This is a continuous graph. And what do you suppose the difference is between the two of them? My discontinuous graph, I have just points, right? Whole bunch of points. They're consistent with each other, right? They go in a line. But they're not connected at all. They're just discontinuous, right? They're not connected to each other. You can't continue. Whereas over here, my curve is all connected, right? All points of that are all connected to each other. Okay, so we're going to look at domain and range. So my domain here, whenever I do my domain and range, I want to start my domain with my minimum and end with my maximum. Same with my range. So my smallest number over here, I'm going to just put this first point in here. So I've got -2, 1, 2, 3, 4, 5, -5. -2, whoops, -5. That's my first point. So my first point of my domain, the one that's furthest to the left, is -2. What's my next value then? My next x goes up here just at -1, right? My next one's at 0, 1, 2, and then I end at 3. Okay, that is my domain. Those 6 numbers are my domain. Now when I'm talking about range, I'm starting with my smallest y value going to my biggest y value. So my first one is -5. What's my value at -1? Well, when my x is at -1, 1, 2, 3, y is at -3. And I'm going to follow the pattern. It's going up by 2 every time, right? So then I'm going to have -1, +1, +3, and +5. In this example, if I'm asking for domain and range, right, this is what I expect you to write. My domain, I'm just listing it out. My range, I'm listing it out. That's all I'm asking you to do, is to identify, well, what are all of my possible x values and what are all of my possible y values. Okay, so then our continuous graph over here is going to look a little different. So we're gonna look for our domain. Okay, and doesn't really show up well here, right? But this is -5 over here. This is +5 over here. So my domain are all of my possible x values. My domain is across the x-axis, or the horizontal part of my axis. So my graph, in this case, goes between -5 and +5, right? So this is where we're going to pull in our inequalities that we just talked about last chapter. My minimum is -5. And I know that my x value is going to be greater than or equal to that, but it also needs to be less than or equal to +5. So my domain in this case is -5 is less than or equal to x is less than or equal to 5. Now the difference between these two graphs, right? This is a continuous, this is a discontinuous. My continuous graph tells me, well, it's between -5 and +5 because could I have, for example, I don't know, like -1.5? Yeah, I can. That's part of my graph. It's in the range. And so instead of listing out literally every single small number that falls between -5 and +5, I'm telling you that my domain is any value between -5 and +5. Any value at all. So then my range, I'm looking at my minimum and my maximum y values. So if I look at this graph, this one's pretty funky in that it continues like this for eternity. So it oscillates, which means that it goes up and down between two values all the time. So my minimum is down here at -1. My maximum is up here at +1. So my range, my y values on the horizontal part of my graph is going to be -1 is less than or equal to y, not x, because these are my y values, is less than or equal to +1. So my domain and my range look a little bit different with a continuous graph than it does with a discontinuous graph, right? With a discontinuous graph, I'm just listing out numbers because I just have separate points. But with a continuous graph, since it's all connected, I need to account for every single fraction of a point on this line, right? I'm not just saying, well, my domain is that my x's can just be the whole numbers. Well, that's not true. My x can be any of these numbers in between -5 and +5. And so that's why I'm accounting for all of that way. Okay, just a couple more things, and then we'll be done with this one. So the function c equals 6t plus 8 represents the cost c for t-shirts plus shipping. So I need to identify the independent variable and the dependent variable first. So my independent variable, oh, come on. sudden. E. Oh my goodness gracious, golly gosh. Okay. Independent. And dependent. Okay, so when I'm trying to identify my independent variables and my dependent variables, it's helpful for me to think about the situation that I'm dealing with, right? So in this case, my C is my cost, my T is the number of shirts that I'm making. So what this is saying is that I have to think about, well, does the number of shirts that I have depend on the cost for the total cost for these shirts? Or does my total cost depend on how many shirts I have made? Well, it's maybe a little bit confusing to think about that, but my total cost depends on how many shirts that I've made, right? When the total shirts that I have made goes up, so does my cost. So my dependent variable, the one that depends on the other one, is C, my cost. Cost depends on how many shirts I have. So my independent variable is T, my shirts. How many shirts I have changes what my cost is, right? So it's my independent and dependent variable. So then it's telling me, well, my domain is 1, 2, 3, 4, and 5. What's my range? Well, when I want to figure out my range, I'm going to plug this in, right? So I'm going to take 1 first. And take 1 and plug it into this equation here, right? So 1 times 6 is 6, plus 8 is 14. So when x is 1, y is 14. Or when t is 1, c is 14. Okay? When it is 2, 2 times 6 is 12, plus 8 is 20. What's nice about linear functions like this is linear functions increase or decrease at a consistent rate. That means that it's going to increase by the same amount every single time. So in this case, to get from 14 to 20, I have to add 6, right? So that means from 2 to 3, I need to add another 6. So my next value is 26. I need to add 6 more. So my next value then is 32. And then my last one will be 6 more than that, 38. Because it's consistent, I can just continue the pattern. We'll have another practice one of those. Okay, this next one is that we need to make an input-output table for the function y equals negative 2x plus 3 using the following inputs. So I'm going to put my x's up here, put my y's down there, negative 2, 0, 2, and 4. Okay, so all that I need to do is that I need to take my inputs, plug them into my function, and then see what I get out of it. So my first value is negative 2. So I'm going to plug negative 2 into this equation. Negative 2 times 2, negative 2, sorry, negative 2 times negative 2 is a positive 4. Positive 4 plus 3 is 7. Do the same thing with 0. Negative 2 times 0 plus 3 is a positive 3. 2 times negative 2 is negative 4, plus 3 is a negative 1. 4 times negative 2 is a negative 8. Negative 8 plus 3 is negative 5. That is my input-output table for that function. Okay, last one on this page. The function a equals 14 minus 4b represents the number of avocados you have left after making b batches of guacamole. So the first thing I need to do is identify what are my independent and dependent variables. Independent and dependent. So if you think about this, does the batches of guacamole that I have made depend on how many avocados I have left? Or does how many avocados I have left depend on how many batches I have made? Well, the amount of avocados I have left depends on how many batches of guacamole I have made, right? So my dependent variable is A, my avocados, and B is my independent variable, my batches. So then I'm looking at if my domain is 0, 1, 2, and 3, what's my range? Well, when b is 0, a is 14. When b is 1, a is 14 minus 4 is 10. Right? I'm decreasing by 4 every time. So when b is 2, it's going to be 6. My last one will be 2. Whew, 2. All right, that is going to be all for today.